Hello, I'm Béla Frohn. I'm a PhD student at the Max Planck Institute of Biochemistry, and I'm going to present the first half of the MaxQuant basics, so the basic workflow of MaxQuant. And there are longer videos on this topic on YouTube, which you can find here, so from 2 years ago and from 3 years ago, which cover the same as this talk, but in a bit more detail. So this course is relatively short compared to these ones, and if you want to know more, then go here. So I guess most of the people here already know what MaxQuant is, but still let me quickly introduce the software. So MaxQuant is a software for the analysis of shotgun proteomics data. We can do DDA, so data dependent acquisition, and DIA, so data independent acquisition. It is developed continuously since 2007, and we have a very large user base, which you can see here in the citations. So they grow. This is citations per year, so it's not cumulative, but even per year the number of citations is still growing. And as you already could see if you wanted in the previous videos, it runs on Linux and Windows. You should already know now how to run it on Linux and Windows. And of course it is freely available for everyone who wants, so you don't have to pay for it. So MaxQuant does not come alone, but MaxQuant comes together with its sibling software with Perseus. So MaxQuant is mostly there for the analysis of the raw MS data, and in the end you get some kind of output table which you can then put into Perseus, and there you can do all the interesting bioinformatic analysis and statistics and whatever you want to do. So MaxQuant deals with the raw data you get from your machine, and then Perseus deals with the output from MaxQuant, and there you can do interesting analysis. So here in these pre-courses we will deal with MaxQuant, and in the summer school there will be a lot more about Perseus. So if you want to know more about how Perseus works, how MS data analysis works, and so on, you can have a look at this review here from our group, which is really long, really comprehensive, and really good. And if you're just interested in the protocol, so how to use MaxQuant, there is a protocol available here. The most important part of this protocol basically is this table, or this box. Because in MaxQuant there are super many parameters which you can define, but most of them you can just keep the default, and these parameters here are the parameters which you actually have to look at. So this is the table you should at least once in your lifetime as a mass spectrometry researcher have looked at. And now for the rest of this tutorial, I'm going to talk about the basic workflow of MaxQuant, and this is just the first part of this tutorial, so I will cover here in MaxQuant Basics 1 these first steps of the workflow, and then in the following video Daniela will talk about the last 4 steps of the MaxQuant workflow. And as you can see, MaxQuant is really straightforward, so it does one step after the other, so it's really nice to validate what it's doing if you understand what's happening here. So we will now try step by step to understand what's happening inside each of these boxes here. So let's first start with the feature detection. The feature detection, what do we want to do there? So now what we get as input first from the machine is some kind of spectrum. So what is mass spectrometry? We get a spectrum here of masses, or mass to charge ratio. And what we did this with peptides, so we have many peptides, they have different masses and different charges, and depending on what peptide we have, we now get different peaks here at this on this axis. So for every mass and every charge there is one peak, but the same protein or the same peptide, after it was cut into the protein was cut into pieces, can have different peaks or can have multiple peaks, because inside one peptide there can be different isotopes. So in nature these atoms here can sometimes to a low chance have a different mass, so a slightly higher mass. And we observe this here in these isotope patterns. So for the same peptide, we get multiple peaks, and they will be roughly here separated by the same distance. And this distance represents like one change here in mass, so one more here. And of course, from our raw data, we get not only one of these spectra, but many, and we get them in 3 dimensions, not only 2 dimensions. So the height here is the intensity, so how many did we get there at this position? And we don't only have the mass to charge ratio, which is here the same axis, but we also have the retention time. So overall, it will be in 3 dimensions here, and we will have 3-dimensional peaks. So this would be one 3-dimensional peak here, this guy. And then we have many 3-dimensional peaks because we have isotopes. Now this is what we get from the machine, and what we want to do now, so what the feature detection actually is that first of all from the data we want to find out where such peaks are, because so far we only have raw data, so we don't actually know what a peak is. And then we want to find out, okay, this is one peak and this is one peak. Do they come from the same peptide? So are they one isotope pattern? So in the end, we want to have a group of peaks which we assume come from the same peptide. And this is feature detection. So how does it work? This is what we get as input. And now as a first step, we want to find peaks on here, this mass to charge axis. So we have data points on this axis, and they describe something like a peak. And what we basically do is that we define some limits of this peak, which is either between the first 2 data points where one is 0 and the other one is not 0, basically, so these guys here. Or if there are 2 neighboring peaks, it's the first peak that goes up again is not counted as belonging to this side here anymore. So this data point here is lower than this one, but this one here is higher, so here is our cutoff value. So we say then this here is one peak, or this here is one peak, which is a relatively simple approach. And then we find the middle here, and this will then be our center of this peak, so this green line here. And this we assume is the mass to charge ratio for this one peak here. And we have this, of course, for many peaks. So we have this for the different isotopes, so in this axis. And we also have this for the many retention time measurements. So we have many of these peaks here, one after another over the retention time here. So these are then 3D peaks. So 2 dimension first, and then 3rd dimension added as retention time. So what we get then here are many such things, and we can put them together to one 3-dimensional peak, where you can see here in the middle, this is always this green line here, the center kind of the peak, and this outline here is this 2 outer lines here. And of course there's a clever algorithm which decides if something belongs together or not. So basically we always look at the next retention time scan and see if it somehow looks similar. So if the difference in mass is less than 7 parts per million. And because sometimes there might be a gap in the retention time scan, we also consider the next nearest scan. So after all, we get for each 3-dimensional peak here, we get one of these 3-dimensional peaks here. So we get many of them. And so now what we have is many peaks, but we don't know yet if which of them belong to one isotope pattern. So we somehow have to cluster or to find out which peaks of the ones we found belong together. And of course, we know that they should be separated by roughly 1 over the charge. So this should be the difference on the mass to charge ratio axis. So this is something we can take into account. but there are some other criteria we can take into account. So, for example, very important is that the overall profile over the retention time should look the same for every peak. And taking into account these different criteria, we can define which of our peaks belong together and which of them belong thus to one isotope pattern. And of course, if we have something like SILAC, so we have one MS1 label pair or even more than a pair, so maybe triples, we can do basically the same for a longer distance. So we should roughly know the mass difference. So we should more or less know how these two islands here are separated. And then, of course, these isotope patterns should be correlated. And, of course, here again, the profile over the retention time should be correlated. So again, a clever algorithm taking this into account can find out which label pairs belong together. So now from our raw data, we found out which peaks belong to the same isotope pattern and which isotope patterns belong to the same label pair. So basically, we now have many peaks which we say they should all come from the same peptide. And this is what we're interested in because we want to identify peptides, right? So before we did this, we had unlabeled data points where we didn't know where they come from. And now we still don't know where they come from, so we don't know the peptide sequence, of course, but we can at least say these guys here, they all belong together, or these guys here, they all belong together. So they should come from the same peptide. We don't know the peptide yet, but at least we know that all these guys here belong together. And this is the result of the feature detection. So one more thing, this is really important and crucial about the feature detection, is that we now, as we have many peaks here, so over the retention time, over mass to charge ratio and different pairs and so on, we have really, really many data points for the mass estimate. Because what we eventually want to do is we want to know how heavy is the peptide which we measured here in proportion to the charge. And then we can somehow figure out which peptide might have originated to this, or might have given origin to this thingy here. So what we want to find out is the mass. And as we have now many data points for this mass, we can do some basic statistics on it. So we can say, okay, all these data points, we can basically put together and calculate a very precise mean for this, which should give us a very good estimate of what the mass of our peptide actually is, because all these data points here should come from the same peptide. And also, as we have many data points, we can calculate basic statistics for the deviation. So we can calculate the variance or the standard deviation on how good we estimated this mass. So this is really interesting because we will, on these descriptive statistics like the mean and the standard deviation, we will base our algorithm that searches for a peptide which might have given origin to this pattern. Okay, so this was the feature detection, and now we will try a first search, which means that we will search for peptides from a database which might have given origin to the patterns or to the features which we found. So we want to now identify which peptide might be the origin of my feature. So what we have is here we have our unlabeled features where we know that some of them belong together, and as previously mentioned, we have estimated masses and we have variances or standard deviations of these masses which we estimated. So now for all these guys here, for all these features, we say, okay, now I take my estimated mass, and based on this mass, I look up in some kind of database which peptides might have given rise to this feature here, to this spectrum. So this is a database. The search is based on the Andromeda search engine, which there will be a separate talk about, so I will not cover it here in detail. But basically, this database stores theoretical M2 spectra. And what we do is that we take the M2 spectra which we measured here and compare them to the spectra of the database. And then we take the best hit and basically say, okay, the best hit is this peptide. And for the first search, we basically just do this by a cutoff threshold where we say, okay, the hit has to be good enough, so better than this or that. So we identify this as the peptide we found here. And now the important point is that this search in the database is not like the whole database that is searched, because this would take forever basically to search. But we only search a very small subspace of the database. And which subspace of the database we search is based on the mass, because we ordered our database by mass from low mass to high mass. So as we estimated in mass here, we should know more or less where in our database we have to look. And then we define a window in which we want to look. And this window, again, is based on the variance or the standard deviation which we found earlier. So this gives us information about where we should look in our database. And of course, this is very crucial. If we found a wrong, or if we estimated a wrong mass here, then we look at a very wrong point in the database or region in the database, so we won't find a good hit. So estimating the correct mass here is crucial to identifying the correct peptide from the database. Okay, so now in our first search, we found peptides for some of our features here, but not for all. And now we can label some of our things here we have, for example, the blue one here. We know, okay, this should be this or that peptide, but for others we might not know yet. And this is why we do now the recalibration. So what is recalibration? Basically, this space here where we defined our features, or where we found our features, is a two-dimensional plane. So one axis is the mass over charge axis, and the other one is the retention time axis. And there are these spectra over retention time, which should, in theory, be a straight line, because the mass of the peptide should not change. But in practice, this here is wobbling around and is more like very curvy. For example, or the origin most of the time is that the temperature the machine stands in, of the room the machine stands in, is changing because someone opens the door or whatever. So this here is curvy, and this will first of all result in, or might result in a wrong estimate of the mass, which is bad, as we have seen just now. And of course, it will give us a higher variance or standard deviation. So the window we have to look in our database is larger, so this will take longer. And you can see here the error in parts per million of the mass. So here 0 would be the correct mass, and we see that the error, so here on the left side it's over retention time, and here it's over mass to charge ratio, that the error here somehow wobbles around in a completely non-linear way. So what we're going to do now is that for some of our features we found out by the first search which peptides they should come from, and for these peptides we know which mass they have. So what we can do now is that we somehow stretch or smash together the space here, this two-dimensional plane, in a nonlinear way, such that the spectra which we identified in our first search are actually at the correct position, and that they are in one line. So this will then change in a nonlinear way our plane here, but give us much nicer and more like in one line assembled features here. And this is the recalibration, and this of course will not only change the features which we already identified, but also the ones which we did not identify before. And the idea is that these spectra which we could not identify before via the recalibration are now at the correct position and have less error, less variance, and so on. So it might be better or easier now to identify them. And we can see the effect on the error here if we plot the same again after the recalibration, and we can see that there is basically no systematic error anymore. So the error is centered nicely at 0, and you can see the same here. So the blue one is afterwards. So the error is centered nicely at 0 and more or less Gaussian. So we have a non-systematic error here before, whereas before it was totally here stretched to the right and definitely systematic error. So our recalibration gives us more or less random error. And after that, we can do our second search, which should now result in a much better peptide identification. And this is the end of this first lecture or first introduction of the MaxQuant basics. And now in the second video, Daniela will continue with the second part of the workflow. Thank you very much.